What if you could observe the entire life of the universe as if it were the tale of a single existence, from its birth to its possible end? Most of us look up at the sky and wonder about the origin of everything we know, but very few think about the ultimate fate of the cosmos and the extraordinary events that occur between those two extremes. The universe has gone through, and will go through, transformations so radical that the concepts of time, matter, and energy take on completely different meanings throughout its eras. Why does the universe have well-defined stages? And how is it possible that everything that exists today, from galaxies to our own bodies, is just a chapter in a cosmic cycle much larger than we can imagine? To understand the magnitude of the universe, we must step away from our everyday view and contemplate its history as a sequence of great eras, each dominated by unique physical laws and processes. Just as a person's life has childhood, maturity, and old age, the universe experiences phases in which its structure, composition, and energy change. But what are those chapters? What invisible forces have shaped the universe since its earliest moments, and what mysteries still challenge our understanding? These questions invite us to explore not only the past, but also the distant future, where the strangest destinies await matter and energy. Over billions of years, the universe has gone through episodes so extreme that they challenge our imagination. There was a time when all matter was compressed into a fraction of a second, where the physical laws we know today simply did not exist. Then, fundamental particles emerged, atoms formed, and much later, stars and galaxies. However, each of these stages is just a page in a cosmic book that is still being written. Did you know that in the future, there could come an era so cold and dark that no star will ever shine again? Or that the very fabric of space-time could tear apart, putting an end to all known structure? These scenarios, although they may seem straight out of science fiction, are the subject of scientific studies and theories that seek to answer the deepest questions about the fate of the cosmos. The history of the universe is, in fact, the story of transformations and cycles, of births and deaths on unimaginable scales. Understanding the eras of the universe is to peek into the greatest tale ever told, where each phenomenon, from the Big Bang to the possible disintegration of matter, reveals a fundamental piece of the cosmic puzzle. How far will this journey go? Is it possible that, after all, the universe does not have a definitive end, but is part of an eternal cycle of death and rebirth? Join me in discovering how, by contemplating the eras of the universe, we can understand not only the distant past, but also the future that awaits everything that exists. What does it really mean for the universe to have an origin? To understand this, we must go back to the moment when time and space, as we know them, simply did not exist. Before the birth of the universe, there was neither matter nor energy, not even a vacuum. The concept of before did not exist because time itself had not yet begun its march. It's like trying to find absolute north on Earth. No matter how far we go, there will come a point where there is simply no more north. Thus, the origin of the universe represents the north of time and space. But how can something arise from nothing? Scientists have concluded, based on solid observations and theories, that the universe was born in an event known as the Big Bang. This was not an explosion in a particular place, but the sudden emergence of all space and time, expanding from an extremely dense and hot state. If we could compress all the matter and energy of the cosmos into a single infinitesimal point, we would have what is known as a singularity, a concept that completely challenges our intuition and the laws of physics that govern our day-to-day lives. And how can we be sure that the universe had a beginning? The most compelling evidence is the very expansion of the cosmos. If we rewind the cosmic film, galaxies come together to meet at a common point. Furthermore, the cosmic microwave background radiation, a kind of thermal echo of the primitive universe, confirms that billions of years ago, everything was much hotter and more compact. It's like hearing the echo of a voice in a cave and deducing how deep it is. only here, the scale is unimaginably greater. The birth of time and space marks an absolute limit to our knowledge. No matter how far science advances, it is impossible to know what was before the Big Bang, because that before simply does not exist. Everything we know, from the physical laws to the atoms in our bodies, emerged from that initial moment. This idea, as perplexing as it is fascinating, is one of the greatest mysteries of existence and continues to inspire scientists and philosophers alike. Are we facing a cosmic chance, or are there even deeper laws waiting to be discovered? The answer, for now, remains as mysterious as the origin of the universe itself.
If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey.
What happened in the first moment of the universe? To answer this question, we must go back to a time so remote that it challenges human understanding: the Planck era. This period spans from the very birth of the universe to an unimaginably tiny fraction of a second later, approximately 10 to the power of negative 43 seconds. To give you an idea, if the universe were a 1,000-page book, the Planck era would occupy barely the first letter of the prologue. Everything we know about space, time, and matter begins here, where ordinary rules cease to make sense. During the Planck era, the four fundamental forces of nature were unified into a single primordial force. There was no distinction between gravity, electromagnetism, or the nuclear forces. What would a universe look like where everything is so compressed that the differences between these forces simply do not exist? The temperature and density were so extreme that conventional physics, as we know it, cannot describe what was happening. The equations of general relativity and quantum mechanics, although powerful, fail when trying to explain this period. It's like trying to describe an ocean with the rules of a puddle. Can we know anything about what was happening in that instant? Scientists have proposed that the entire universe, all the energy and matter that exists, was concentrated in a single tiny point, smaller than a subatomic particle. The reality was so chaotic and fluctuating that space and time themselves were not defined in the way we understand today. Imagine a sea of quantum foam, where the laws that govern our world simply do not apply. The concepts of before and after, here and there, fade away. It is a scenario where human intuition falls short, and only the most abstract mathematics dares to explore. Why is the Planck era so mysterious? Because there is still no theory capable of unifying gravity with quantum mechanics, a dream known as the quantum theory of gravity. Solving this enigma would allow us to understand the zero moment of the universe, the starting point of absolutely everything that exists. In fact, physicists are searching in the oldest echoes of the cosmos, in gravitational waves and the behavior of elementary particles, for clues that may reveal the secrets of that instant. The Planck era is, in essence, the ultimate frontier of human knowledge, a period that reminds us how much is left to discover about our deepest origins. What would happen if the universe, in an infinitesimal fraction of a second, grew from a microscopic size to something billions of times larger? That precisely is what the theory of cosmic inflation proposes. But how is it possible that the cosmos experienced such a dizzying expansion in such a short time? To understand it, let's imagine a balloon that has just begun to inflate. In an almost imperceptible moment, it goes from being invisible to occupying a considerable space. However, in the case of the universe, that moment was even briefer, less than a trillionth of a second after the origin. Space expanded at a rate that defies intuition. Cosmic inflation solves several of the big questions about the early universe. For example, why does the universe appear so uniform in all directions? If we think of two opposite points in the cosmos, separated by unimaginable distances, how is it possible that they have practically the same temperature and composition? Without inflation, these points would never have had time to agree. But thanks to this ultra-fast expansion, regions that were very close could move away at incredible speeds, maintaining the same physical properties. Thus, inflation explains the homogeneity and isotropy that we observe in the current universe. But not everything is uniform. Inflation is also responsible for the small quantum fluctuations that, amplified by this expansion, sowed the seeds of all cosmic structure. Have you ever seen the small waves that form on the surface of a pond when a drop falls? Similarly, during inflation, tiny quantum irregularities in the fabric of space-time were stretched to astronomical scales. Over time, those fluctuations became the galaxies, stars, and planets, that is, everything that exists today. The inevitable question is, what caused inflation and why did it stop? The answer remains one of the greatest mysteries of modern cosmology. It is suspected that an energy field, known as the inflaton field, was responsible for this enormous expansion. When the energy of the field decreased, inflation ended abruptly, giving way to a much larger and expanding universe, full of energy and matter. From that moment on, the development of the complex and fascinating cosmic history would begin, which, millions of years later, would allow us to question our own origins. What would happen if the forces that govern every corner of the universe were actually one? In the era of grand unification, just a fraction of a second after the origin of the cosmos, the universe reached unimaginable temperatures, much greater than those at the core of any star. At that moment, the three fundamental forces we know today, the strong nuclear force, the weak nuclear force, and the electromagnetic force, were not separate. They were like the threads of a single rope, fused into one superforce. How do we know this? Theoretical physics and experiments in particle accelerators give us clues, although recreating those extreme conditions remains beyond the reach of human technology. Have you ever wondered why there are different forces in nature? During this time, the universe was so compact and hot that the energy was enough to erase the differences between them. As the universe expanded and cooled, a fundamental phenomenon occurred. The original symmetry began to break. It's like having a perfect ice block that, as it melts, divides into distinct shapes. Thus, the strong force separated, taking its own path, while leaving the other two still united. This process, known as symmetry breaking, is responsible for the distinct forces that govern matter and energy today. But what consequences did this separation have for the future of the universe? The release of enormous amounts of energy during the symmetry breaking seeded the cosmos with exotic and unstable particles, some of which would be essential for the formation of matter. Furthermore, the separation of the strong force allowed for the existence of quarks, which would later combine to form protons and neutrons, the fundamental building blocks of atoms. Without this event, matter as we know it would never have existed. The era of grand unification is one of the great mysteries of modern physics. Although we cannot observe it directly, the traces of this moment are inscribed in the laws of nature and in the patterns of matter that surround us. Advanced theories, such as supersymmetry and hypotheses of yet undiscovered particles, seek to explain exactly how this separation occurred. The universe, in those early moments, underwent such a profound transformation that it planted the seeds of all the cosmic diversity we would see later. Will it ever be possible to recreate that primordial unification in the lab and definitively answer the question of why forces exist as we know them? The search continues. What makes matter and light so different if at their core, both arise from the same cosmic origin? To answer this question, we must travel to a fraction of a second after the birth of the universe, to a moment known as the electroweak era. During this period, the universe was an incredibly hot and dense ocean, where the fundamental forces we know today were not yet completely separated. But what does this really mean? How can a single force divide and give rise to phenomena as distinct as electricity, magnetism, and radioactivity? During the electroweak era, the temperature of the universe was so high that the electromagnetic force and the weak nuclear force were indistinguishable. They acted as a single superforce. It's as if, by heating a metal, its properties change and become unrecognizable until the temperature drops. Something similar happened here. As the universe expanded and cooled, around a billionth of a second after the Big Bang, the energy dropped enough for this force to separate into two different entities. Thus, the electromagnetic force was born, responsible for light and all electrical and magnetic interactions, and the weak force, fundamental for certain types of radioactivity and nuclear processes. But why is this division so relevant? The separation of the electroweak force marked a turning point in the history of the cosmos. It allowed elementary particles to begin behaving in new and diverse ways. For example, thanks to the weak force, neutrons within atomic nuclei can decay, giving rise to other elements. Without this process, stars like the Sun could not shine, and life as we know it simply would not exist. On the other hand, the electromagnetic force is responsible for light traveling through space, allowing us to observe the universe even billions of years after the events. Today, physicists have managed to recreate the conditions of the electroweak era in laboratories like the Large Hadron Collider, albeit only for tiny fractions of a second. This has allowed us to better understand how, at extremely high temperatures, forces unify and the universe behaves in radically different ways. Thus, the electroweak era is not just a lost chapter in cosmic history, but a reminder that, in the early moments, the fundamental forces were one, waiting for the right moment to reveal their diversity and give rise to the universe as we know it. Can you imagine a universe where light and radioactivity were consequences of a single force? That was the fleeting scenario of the electroweak era, a decisive moment that allowed, over time, for matter, stars, and ultimately, ourselves to emerge. The evolution of the cosmos is marked by these moments of separation and transformation, where the simple gives way to the complex, and where each change in the fundamental laws opens the door to new possibilities in the history of the universe. What happened when the universe was less than a second old? In that unimaginably hot and dense moment, the cosmos was like a great primordial soup where nothing resembled what we know today. There were no atoms, no stars, not even protons or neutrons. Only a chaotic sea of pure energy existed, where elementary particles began to emerge. But what were the first particles to appear, and why are they so important? As the universe expanded and cooled rapidly, that energy began to transform into matter. In this process, quarks, electrons, and neutrinos emerged. Quarks are like the fundamental building blocks of matter. Later on, they would join together to form protons and neutrons, but at this moment, they existed freely, constantly colliding with each other at incredible speeds. Electrons, for their part, are the particles that would later allow for the formation of atoms and, ultimately, everything we see around us. And neutrinos? They are almost ghostly particles, so light and elusive that they pass through matter practically without a trace, but their presence was overwhelming in those early moments. Why don't we see these free particles in our day-to-day lives? The answer lies in the extreme conditions of that early universe. Imagine a cosmic pressure cooker, where the temperature was so high that particles could only exist alone for fractions of a second before interacting and transforming. If we tried to recreate those conditions today, we would need gigantic particle accelerators, and even then, we would barely catch a glimpse of what was happening in those first moments of time. The formation of elementary particles was like the first sketch of the great cosmic building. Each one played a key role in the subsequent evolution of the universe. Without quarks, there would be no atomic nuclei. Without electrons, atoms would be impossible. Without neutrinos, many nuclear processes would make no sense. This ballet of particles, governed by the laws of quantum physics, laid the groundwork for all the complexity that followed. Who would have thought that everything that exists, from galaxies to human beings, began thanks to these fundamental ingredients and the extreme conditions of a newborn universe. What happens when the universe, still young and in the midst of an expansion frenzy, begins to cool down enough to allow the emergence of more complex structures? Thus begins the era of hadrons, an essential chapter in cosmic history. During this period, the universe is no longer just a sea of elementary particles, but starts to consolidate the true building blocks of matter, hadrons. But what exactly are hadrons, and why are they so crucial? Hadrons are composite particles, formed by the union of quarks, those even smaller particles that combine in specific ways. Protons and neutrons, for example, are hadrons, and they will be the protagonists of the ordinary matter we know. During this era, which occurred just fractions of a second after the origin of the universe, the heat was so extreme that quarks and gluons, responsible for binding them, were in a free state, like loose ingredients in a boiling soup. However, as the environment cooled, these ingredients began to unite thanks to the strong nuclear force, the most powerful of the four fundamental forces. Did you know that at this moment, the universe was so dense and energetic that every collision between particles was an opportunity to form something new? Quarks grouped into trios to give rise to protons and neutrons, while antiparticles also made their appearance. But here arises another fascinating question. If for every particle there was an antiparticle, why didn't the universe disappear in an explosion of pure energy? The mystery of the asymmetry between matter and antimatter remains one of the great enigmas of physics, but thanks to a slight imbalance in favor of matter, hadrons survived and laid the foundations for everything that exists. As the era of hadrons progressed, the universe continued to expand and cool. Protons and neutrons, now more stable, began to dominate the landscape. However, those that did not manage to combine soon disintegrated into lighter particles. This delicate process was essential because only the most stable hadrons persisted long enough to later allow the formation of atomic nuclei. In other words, without the era of hadrons, atoms, stars, and even ourselves simply would not exist. In summary, the era of hadrons is the stage where matter begins to take real shape, as if the universe were assembling the pieces of a gigantic puzzle. Each hadron formed during this period represents a victory over primordial chaos and a fundamental step towards complexity. The next time you think about the atoms that make you up, remember that it all started here when quarks learned to work together. Isn't it amazing to think that, at our core, we are the result of a cosmic choreography initiated billions of years ago? What happens when the universe cools down enough for electrons and neutrinos to take center stage? We delve into the so-called era of leptons, a fascinating and critical stage in cosmic history. But why is this period so special? To understand it, let's think of leptons as the main actors in a play where the temperature is still too high for protons and neutrons to form atoms, but low enough that quarks are no longer the stars. Here, electrons, positrons, and neutrinos dominate the stage, interacting intensely in a sea of energy. The era of leptons begins when the universe is just a few seconds old and at a temperature of billions of degrees. In this extreme environment, collisions between particles are so frequent that electrons and positrons are created and destroyed at a dizzying rate, like bubbles in boiling water. Neutrinos, on the other hand, begin to decouple from the rest of the matter, traveling almost unimpeded through the cosmos. Did you know that these primordial neutrinos still exist and constantly pass through everything we know, even our own bodies, without us being able to easily detect them? During this era, the energy density continues to decrease, leading to a crucial moment: the massive annihilation of electrons and positrons. When the temperature drops sufficiently, most of these pairs annihilate each other, releasing a tremendous amount of photons. This process has profound consequences, as it increases the ratio of photons to protons and neutrons, a number that continues to define the properties of the current universe. Have you ever wondered why there is so much more light than matter in the cosmos? The answer lies in this fleeting moment when leptons relinquish their dominance to heavier particles. But what about neutrinos? Here, something extraordinary happens. As they stop interacting with other particles, neutrinos become frozen in the universe, forming a cosmic neutrino background as ancient as time itself. Unlike the cosmic microwave background, these neutrinos are nearly impossible to detect, but their existence is fundamental to understanding the subsequent evolution of the universe. Thus, the era of leptons marks the end of the reign of light particles and the transition to new stages, where matter begins to organize and lay the groundwork for the formation of atoms, stars, and galaxies. What if I told you there was a time when radiation was the absolute sovereign of the universe? That's right. During the era of radiation, the energy of the cosmos was in the hands of photons and other light particles, which dominated the cosmic stage far more than matter. But how did we arrive at this strange energetic domain? And why was it so crucial for the development of everything we know today? During the first few 100,000 years after the birth of the universe, the temperature was so unimaginably high that matter could barely exist in the form of free particles. Photons, those light particles we now associate with a simple light bulb, were the true protagonists then. Their energy was so intense that any attempt to bond protons, neutrons, and electrons was quickly destroyed. In other words, the universe was like a boiling cauldron of radiation, where matter could barely withstand the onslaught of an endless energetic tide. What did this domain of radiation really consist of? If we could visit that moment, we would discover that every cubic centimeter of the universe housed billions of photons, interacting and colliding with particles of matter. The energy density was so great that the gravity of matter could barely influence the evolution of the cosmos. Everything depended on the behavior of radiation. Interestingly, this period was essential for the universe to expand and cool enough for matter to eventually take center stage and form atoms, stars, and galaxies. Now, why was the era of radiation so decisive for the fate of the universe? The answer lies in the rate at which radiation loses influence as the universe expands. Thanks to the expansion itself, photons lose energy and radiation weakens. This slowdown eventually allowed matter to take control, laying the groundwork for the formation of complex structures. If radiation had continued to dominate, the universe would never have allowed for the existence of planets, life, or even questions like this. Did you know that the radiation that dominated the universe in that era is still present today, although much colder and weaker? Today, we detect it as the cosmic microwave background, a faint echo of that time when light was the undisputed queen. Thus, the era of radiation not only set the pace and rules for the birth of the first structures, but also left an indelible mark, a silent message traveling through space, reminding us of the energetic origins of our cosmos. When and how did the first atomic nuclei of the universe form? To answer this question, we must go back to a time when the cosmos was a boiling ocean of elementary particles and radiation. Only a few minutes had passed since the beginning of time, and the density and temperature were so extreme that matter, as we know it, simply could not exist. But as the universe continued to expand and cool, a crucial moment arrived: primordial nucleosynthesis. This process, often described as the Great Cosmic Kitchen, was responsible for manufacturing the first basic ingredients of all visible matter. But why could only certain elements form at this early stage? The key lies in the conditions of the universe. When the temperature dropped low enough, protons and neutrons began to join together, like pieces of a puzzle that only fit under very strict rules. Hydrogen, in the form of nuclei called protons, was the first and most abundant. Shortly after, some protons and neutrons managed to form helium nuclei, the second lightest element. In smaller amounts, traces of deuterium, tritium, and lithium were formed. However, the formation of heavier elements was impossible in this environment because the universe cooled too quickly to allow these complex nuclei to assemble. Have you ever wondered why the universe is mostly made of hydrogen and helium? The answer is directly related to this brief but decisive phase. In just a few minutes, primordial nucleosynthesis defined the basic chemistry of the cosmos. Approximately 3/4 of the visible matter remained in the form of hydrogen, and almost all the rest became helium. Lithium and deuterium, while essential for understanding chemical evolution, were relegated to tiny amounts. This ratio was so precise and universal that astronomers use it today as one of the main pieces of evidence supporting the Big Bang model. But how do we know all this if no one was there to witness it? The answer lies in the oldest light of the universe and in the composition of the oldest stars. By analyzing the abundance of these light elements in space, scientists have been able to reconstruct that original recipe. Any deviation in the calculated proportions would indicate an error in our understanding of the primitive universe. Thus, primordial nucleosynthesis was not only the first great act of cosmic alchemy, but also laid the groundwork for everything that would come after: stars, planets, and even life itself. What does it mean that the universe has entered the era of matter? This stage marks a before and after in cosmic history. For a long time, radiation energy was dominant, as if the universe were an ocean of light and particles traveling at extreme speeds. However, as the universe expanded and cooled, the energy of matter, protons, neutrons, electrons, and the first atoms began to surpass that of radiation. It's as if, in a noisy party filled with lights and sounds, suddenly more solid, quieter, and heavier guests entered, who would end up being the stars of the event. Why is this change so important? Because only when matter takes control do the doors to complexity open. Particles are no longer at the mercy of radiation. They can now form stable structures. For the first time, tiny seeds of matter, pulled by gravity, begin to come together. In this way, increasingly dense clouds of gas form, which over time will give rise to galaxies, stars, and planets. It is in this scenario where the universe develops the ability to build, to assemble cosmic bricks from the matter that floats in its vastness. Could we say that the future was born here? In a sense, yes. Without the supremacy of matter, the structures we observe today would never have existed. From a simple speck of interstellar dust to gigantic spiral galaxies. From this moment on, gravity becomes the architect of the universe, gathering and organizing matter into increasingly complex forms. It is a slow but unstoppable process, as if the cosmos had ceased to be a turbulent sea of energy to become a stage where matter can begin to tell its own story. But did you know that during this era, the universe was still a hostile place for life as we know it? Although matter dominated, temperatures remained incredibly high and radiation was still present, albeit in the background. The conditions for the formation of stars and planets were just beginning to take shape. However, the mere fact that matter had taken control meant that the universe finally had the essential ingredients to build everything that would come afterward. The era of matter is, in essence, the starting point of the great cosmic architecture. What happened when the universe was just hundreds of thousands of years old? The answer is surprising. A fundamental phenomenon occurred that allowed light, for the first time, to travel freely through the cosmos. This event is called recombination, and it marked the birth of the first atoms. Until that moment, the universe was an extremely hot and dense place, a true soup of particles, where protons, electrons, and photons constantly collided. Why was it impossible for light to escape? Because every time a photon tried to move forward, it was immediately absorbed or scattered by a charged particle, as if you were trying to run through a crowd so dense that you couldn't take a step without bumping into someone else. However, everything changed when the universe expanded and cooled enough, reaching a temperature close to 3,000 degrees Kelvin. Why was this cooling so crucial? Because it allowed electrons to lose the energy needed to escape from protons, and ultimately to become trapped by them, forming neutral hydrogen atoms. It's as if, on a huge dance floor, couples could finally meet and join together, no longer getting in each other's way. Suddenly, the universe became much more transparent, as photons, instead of constantly colliding, began to travel vast distances without obstacles. Have you ever wondered how we know this happened? The key lies in the cosmic microwave background radiation, that fossil echo that fills the entire universe. Recombination allowed primordial light to be released and travel for billions of years until it reached us, carrying information about that distant time. Every time scientists study this cosmic background, they are literally seeing the imprint of that moment when atoms were born, and the universe became transparent. Recombination not only marked the end of an era dominated by the chaos of free particles, but also opened the door to the formation of the first complex structures. Thanks to the union of electrons and protons, the basic building blocks were created that would one day form stars, planets, and everything we know. Without this process, the universe would have remained dark and opaque, making the existence of light, and therefore life as we understand it, impossible. Thus, recombination was the first step towards a cosmos where matter and light could finally coexist and evolve together. What if there were a photograph of the universe when it was just a few 100,000 years old? Although it may seem like science fiction, something like that exists, the cosmic microwave background. But what exactly is this mysterious echo of the past? It is the residual radiation that fills the entire cosmos, a kind of fingerprint that tells us what the primitive universe was like in its early moments of freedom for light. Approximately 13,800,000,000 years ago, the universe was so dense and hot that photons, the particles of light, could not travel freely, as if you were trying to see through an extremely thick fog. But then, a crucial event occurred. Electrons and protons combined to form hydrogen atoms, allowing light to escape and begin its journey through space. That moment was recorded in the form of a faint radiation, which we now detect as the cosmic microwave background. Why do we call it that? Because due to the expansion of the universe, that original light has cooled to a temperature of just 2.7 degrees above absolute zero, emitting in the microwave region of the electromagnetic spectrum. In other words, it is the fossil glow of the universe, visible in all directions, and one of the strongest pieces of evidence for the Big Bang. Can such an ancient signal reveal secrets about the current universe? Surprisingly, yes. By studying the tiny variations in temperature and density in the cosmic background, scientists have been able to reconstruct the history of matter and energy, as well as calculate the age, composition, and geometry of the universe. It's as if we have access to an ancient map that reveals the seeds of all the galaxies and structures we see today. Even the famous COBE mission, followed by WMAP and Planck, allowed us to detect these tiny fluctuations, confirming theoretical predictions and opening a direct window to the most distant past. Could we exist without the cosmic microwave background? Without this primordial echo, our understanding of the universe would be much more limited. Thanks to its study, we have discovered that the universe is almost perfectly homogeneous, but with slight irregularities that gave rise to everything we know. Moreover, it has allowed us to rule out alternative models to the Big Bang and confirm that we live in an expanding cosmos. Thus, the cosmic microwave background is not only a silent witness of the origin, but also a fundamental tool for unraveling the destiny and evolution of the universe. Have you ever wondered what the universe was like before the first stars appeared? There exists a fascinating and terrifying period in cosmic history known as the Dark Age. After primordial light was freed to travel through space, the universe experienced a long era in which darkness reigned completely. What was happening in this silent and cold abyss? Neutral hydrogen filled the space, and light, although present, found nothing to illuminate. There were no stars, planets, or galaxies, only an invisible haze of atoms floating in the vastness. During this time, the temperature of the universe slowly decreased, as if the entire cosmos were submerged in a deep sleep, waiting to awaken. Matter, driven by tiny fluctuations in density, began to clump together under the power of gravity. It is curious to think that, in that uniform sea of hydrogen, the fate of everything we know was already written in minuscule, almost imperceptible differences. How is it possible that such stillness gave rise to the complexity we observe today? The Dark Age lasted hundreds of millions of years. Why so long? The answer lies in the slowness with which matter condensed. Without visible light sources, the universe was like a completely dark room, where occasionally, in especially dense areas, matter began to gather, setting the stage for the arrival of the first stars. This period was crucial. Without it, the structures we see today, like galaxies and clusters, could not have formed. In a way, darkness was an incubator, a silent laboratory where physics wove the threads of the future. Is there any trace of that time in the current cosmos? Surprisingly, yes. Radio waves from the neutral hydrogen of the Dark Age still travel through space, and astronomers are trying to detect them to reconstruct that invisible chapter of history. Studying the Dark Age is like trying to read the first pages of a book whose beginning was written in invisible ink. Each new discovery brings us closer to understanding how, starting from nothing, light and complexity conquered the original darkness of the universe. What had to happen for the first points of light to appear in a cold and dark universe? The answer lies in the formation of the first stars, known as population 3 stars. These stars marked the end of the so-called Dark Age and radically transformed the cosmos. But how was it possible for giants capable of illuminating the primitive universe to emerge from a diffuse cloud of hydrogen and helium? It all begins with the influence of gravity. Imagine immense clouds of hydrogen, the lightest and most abundant element, floating in an almost empty space. Over millions of years, small fluctuations in density, like wrinkles on a sheet, cause certain regions of these clouds to become slightly denser than others. Gravity acted like an invisible hand, pulling more and more gas toward these points, compressing and heating them. When the temperature and pressure at the center of these regions reached extreme levels, nuclear fusion ignited for the first time. Hydrogen atoms began to fuse, releasing a tremendous amount of energy and giving birth to the first star. One of the most intriguing questions is, what were these first stars like compared to our Sun? It turns out they were cosmic monsters. Population 3 stars were much more massive, some up to hundreds of times larger than the Sun. Lacking heavier elements, their evolution was rapid and violent. Their life was short, lasting only a few million years, but their impact was immense. Upon dying, they exploded in colossal supernovae, seeding the universe with heavier elements like carbon, oxygen, and iron, essential for the formation of planets and, eventually, for life. And why is this process so important? The first stars were the chemical laboratories of the cosmos. Before their appearance, the universe was a simple and monotonous place, composed almost exclusively of hydrogen and helium. It was the explosive death of these stars that enriched space with a palette of elements, allowing future generations of stars, planets, and even living beings to form. In summary, the formation of the first stars not only illuminated the universe, but also forever changed its composition and destiny. Every carbon atom in our bodies, every particle of oxygen we breathe, was forged in the hearts of those first stars. Thus, to ask how they came to be is, in a way, to ask about our own origin in the cosmos. What happened when the first stars ignited their light in the cosmic vastness? After a long period of darkness, the universe underwent a radical transformation known as rionization. This phenomenon, which began a few 100 million years after the origin of the cosmos, marked the end of the so-called Dark Age and the beginning of a new stage in universal evolution. But why is this process so crucial? And how did it forever alter the fate of matter and light? During rionization, the first stars and galaxies released enormous amounts of ultraviolet radiation. energy intense enough to strip electrons from the hydrogen atoms that filled the early universe. This act, akin to lighting billions of beacons in dense fog, caused neutral hydrogen to become ionized plasma, allowing light to travel great distances without being absorbed or scattered. Before this moment, the universe was like a room filled with smoke, where photons were trapped. After ionization, the cosmos became transparent, paving the way for the observation of distant galaxies. Have you ever wondered how we know this event occurred? Astronomers have found clues in the light from distant quasars. By analyzing their spectra, they uncover traces of neutral hydrogen that drop sharply after a certain point in cosmic time. This leap indicates the moment when most of the hydrogen ceased to be neutral and became ionized, a true fingerprint of the change. Additionally, the cosmic microwave background also shows slight alterations that reveal the presence of free electrons, a direct remnant of rionization. Rionization was not just a spectacle of light, but a turning point for the formation of cosmic structures. By allowing light to travel freely, it facilitated gravitational interaction between galaxies and the propagation of energy and matter through space. Without this process, the universe would remain opaque and chaotic, unable to give rise to the diversity of forms we observe today. Essentially, rionization is the transition that transformed the universe into the dynamic and luminous stage that allows for our existence and the exploration of its mysteries. How did the first galaxies in the universe come to be? After the long initial darkness, matter began to clump together, guided by subtle yet powerful gravity. For millions of years, small fluctuations in the density of the cosmos acted as invisible seeds. Where there was a little more matter, gravitational attraction was enough to draw in even more material, forming gigantic clouds of gas and particles. Why didn't all that gas disperse into the vastness of space? Because gravity works like a cosmic net, trapping matter and pushing it to form increasingly complex structures. In this primitive environment, the first galaxies were born as islands of light in a sea of darkness. How do we know this? The most advanced telescopes show us galaxies that existed when the universe was just a few 100 million years old. These early galaxies were much smaller and more chaotic than those we see today. Their shapes were not the elegant spirals we admire now, but irregular and turbulent groupings, filled with dust and enormous clouds of hydrogen. These young galaxies were true stellar nurseries. Within them, matter compressed enough to ignite the first suns, generating enough light to transform the dark universe into a vibrant and dynamic stage. But what role did dark matter play in this process? Although we cannot see it, dark matter acted like an invisible scaffold upon which ordinary matter, the kind that forms stars and planets, accumulated. Without this mysterious component, galaxies could not have formed so soon. Scientists believe that halos of dark matter attracted primordial gas, facilitating the formation of the first galaxies and allowing the emergence of the large cosmic structures we observe today. And why is the birth of galaxies so important? Without these first structures, there would be no stars, no planets, and certainly no life. Galaxies were the laboratories where the heavier elements began to forge in the hearts of stars. Each primitive galaxy was a natural experiment, where extreme physics and the fundamental forces of the universe combined to create everything we know. Thus, the birth of the first galaxies marked the beginning of cosmic architecture, laying the foundations for the evolution of the universe as we understand it today. What happens when hundreds or even thousands of galaxies gather in one place, united by the invisible bond of gravity? This is how galaxy clusters arise, the largest gravitationally bound structures in the universe. But how is it possible for galaxies, separated by millions of light years, to end up grouping together in these cosmic giants? The answer lies in the seeds sown shortly after the birth of the cosmos. Tiny fluctuations in density in primordial matter that, over billions of years, were amplified under the relentless action of gravity. In an expanding universe, matter was not distributed evenly. Some regions contained a slight overdensity of matter, acting as gravitational wells that attracted everything around them, including entire galaxies. You can imagine it like bumps on a stretchy sheet. Marbles would inevitably roll towards the deepest dips. Thus, over time, galaxies began to approach and group together, first forming small groups and later true clusters. These clusters can host anywhere from a few dozen to thousands of galaxies, each containing hundreds of billions of stars. Did you know that most of the mass in galaxy clusters does not come from the galaxies themselves? In fact, visible matter represents only a fraction. The true glue of these cosmic giants is dark matter, that mysterious invisible substance that multiplies the total mass and keeps galaxies bound together despite their colossal distances. Moreover, between the galaxies, there is gas so hot that it emits X-rays, reaching temperatures of tens of millions of degrees. This gas, along with dark matter, creates a sort of atmosphere for the cluster, so dense and energetic that it can influence the evolution of the very galaxies that inhabit it. Galaxy clusters are not only impressive for their size, but also for their role in cosmic history. They are true natural laboratories where galaxies can interact, merge, and even transform. In these environments, galaxies undergo close encounters, gas thefts, and sometimes spectacular collisions that can give rise to new shapes and structures. Observing galaxy clusters is like looking at a vast cosmic city in perpetual construction, where the inhabitants, the galaxies, are in constant change and adaptation. Why is studying galaxy clusters so fascinating for science? Because they are key to understanding the composition and evolution of the universe on a large scale. By analyzing their distribution, mass, and dynamics, astronomers can decipher the amount of dark matter and dark energy present, and even test theories about the ultimate fate of the cosmos. Thus, galaxy clusters become a kind of living archive of universal history, allowing us to read in their depths how the cosmos has changed from its first steps to today. What mysteries lie within the first moments when the universe began to forge the elements that today form planets, stars, and even ourselves? The chemical evolution of the early universe is a process as fascinating as it is fundamental. In the beginning, the cosmos was composed almost exclusively of hydrogen and helium, the simplest and most abundant elements. But how did more complex elements, like carbon, oxygen, or iron, essential for life and the formation of solid worlds, come into being? The answer lies at the heart of stars. The first generations of stars acted as enormous nuclear reactors. In their cores, at inconceivable temperatures and pressures, light atoms began to fuse, forming heavier atoms in a process called stellar nucleosynthesis. Just as a simple recipe evolves into an elaborate dish by adding new ingredients, the universe enriched its chemical menu as stars lived and died. When these stars exhausted their fuel, they exploded as supernovae, scattering their newly forged elements across space. This enriched material would form the basis for new generations of stars and planets, making possible the complex chemistry necessary for life. But why did the oldest stars only contain hydrogen and helium? Because in the primitive universe, the heavier elements did not yet exist. Only through countless cycles of stellar birth and death did the cosmos increase its chemical diversity. The oxygen atoms you breathe, the calcium in your bones, or the silicon in microchips, all were created inside stars that existed long before our sun. Each atom of gold, for example, is the result of titanic collisions between neutron stars, events so powerful that they can release more energy than our sun will emit in its entire lifetime. How far does this process of chemical creation extend? Even today, the universe continues to transform. New stars are born, others die, and elements are constantly being forged. Each galaxy is like a cosmic laboratory where matter is recycled and reinvented. Essentially, the chemical evolution of the early universe is the story of how simple matter gradually transforms into the complexity we observe around us. Everything we know, from the water we drink to distant planets, is the result of this incredible cosmic alchemy driven by stars. What if I told you that a large part of what holds the universe together is something we cannot see, touch, or directly detect? Dark matter is one of the greatest enigmas of modern cosmology. Although it does not emit light or energy, its existence is fundamental to explain how galaxies and the universe as a whole behave. Why do astronomers believe in something so elusive? It all starts with a simple question: why don't galaxies disintegrate due to their own rotation? When scientists observed how galaxies spin, they noticed something extraordinary. The stars at the edges of galaxies move much faster than they should, according to the amount of visible matter. If only the matter we can see existed, those stars would be flung out into space like cyclists on a turn that's too tight. However, they remain bound together, as if some kind of invisible glue is holding them in place. That glue is what we call dark matter. But what exactly is dark matter? No one knows for sure. It is not made up of atoms, does not interact with light, and only reveals its presence through gravity. To imagine its effect, think of a dance floor where you can only see some illuminated dancers, but you notice that there are others moving in the dark because the ones you see change direction or speed unexpectedly. In this way, astronomers infer the existence of dark matter by the way gravity affects stars, galaxies, and galaxy clusters. Dark matter not only holds galaxies together, but it has also been crucial in the formation of the universe's large structures. In the early cosmic moments, it acted as an invisible scaffold, helping ordinary matter clump together to form galaxies and clusters. Without it, the universe would be very different. Galaxies would not exist as we know them, and the cosmos would be a much more uniform and empty place. Despite accounting for about 85% of all the matter in the universe, we still do not know what it is made of. Could dark matter be the key to solving other mysteries of the cosmos? Some scientists believe that if we manage to unveil its nature, we could discover new laws of physics or even clues about hidden dimensions. For now, dark matter remains a silent shadow, indispensable for understanding the evolution and structure of the universe, but still beyond the reach of our direct comprehension. The search for its identity continues, driving some of the most ambitious experiments in modern science. What does it take for planets to be born? The answer may seem simple, but it hides one of the most fascinating and delicate processes in the cosmos. Imagine a gigantic cloud of gas and dust, cold and seemingly inert, floating in deep space. For millions of years, small disturbances, like the shockwave from a distant supernova, can cause these clouds to collapse under their own gravity. This is how protoplanetary disks begin to form around young stars, true nurseries of worlds. What are these first planets made of? The main ingredients are hydrogen, helium, and a small but crucial fraction of heavier elements, such as carbon, oxygen, silicon, and iron. As the disk spins, tiny particles collide and stick together, forming increasingly larger clumps. This process, known as accretion, is like a snowball rolling down a hill. The bigger it gets, the more material it attracts. In a few million years, these blocks can become rocky planets like Earth, or gas giants like Jupiter and Saturn. Where do the conditions for life occur? The answer depends on the distance from the central star. There is a zone called the habitable zone, neither too hot nor too cold, where water can exist in liquid form. However, planetary formation is a chaotic process. Planets migrate, collide, and sometimes get ejected from their system. This cosmic dynamism determines how many planets end up in the right zone to host oceans and potentially life. Is planet formation common in the universe? Recent discoveries of exoplanets have shown us that planetary formation is the norm, not the exception. Thanks to missions like Kepler, we know that almost all stars could have planetary systems, and that there are more planets than stars in the Milky Way. Some systems exhibit unusual architectures, with giant planets very close to their star, or wandering worlds drifting alone through space. The era of planetary formation not only gave rise to the diversity of known worlds, but also made it possible for environments to become stable enough for life in at least one corner of the universe to begin its own story. What makes our sun so special in the vast stage of the cosmos? While it is an ordinary star within the galaxy, its history and that of the solar system are intertwined in a fascinating way. About 4.6 billion years ago, a giant cloud of gas and dust collapsed under its own gravity. A process that, at first glance, might seem chaotic, but is actually the master recipe for the birth of entire planetary systems. In the center of that cloud, the pressure and temperature increased so much that the nuclear oven ignited. Thus, the sun was born, our star. Around that newborn sun, the remnants of gas and dust began to clump together and form small bodies, the so-called planetesimals. How did these fragments become such different planets as the scorching Venus or the gas giant Jupiter? The key lies in the distance from the sun and the composition of the available materials. Closer in, the heat was so intense that only the heavier elements, like iron and silicon, could survive, forming the rocky planets. Further out, the cold allowed lighter elements and ice to come together, giving rise to the giant planets and their moons. The solar system is not just a group of planets orbiting the sun. It also includes asteroid belts, comets traveling from icy regions, and a distant cloud of bodies called the Oort cloud, which surrounds the entire system like a bubble of primordial material. Did you know that every comet that enters the solar system is like a time capsule, preserving clues about the original ingredients of the cloud that gave us birth? In fact, every rock, every grain of dust holds the memory of the first steps of our cosmic neighborhood. Moreover, the sun is much more than just a source of light and heat. Its activity, with cycles of sunspots and explosions called flares, can affect the weather and communications on Earth. But on a much larger scale, the sun is the engine that keeps the solar system together. Its gravity is the invisible bond that directs the dance of planets, asteroids, and comets for billions of years. Without the stability and energy of the sun, Earth would never have been a hospitable place for life. Thus, our solar system is the result of universal processes, but also a unique stage where physics, chemistry, and the possibility of life come together. Is it possible that stardust and primordial gases gave rise to life? This is one of the most fascinating questions in science. Billions of years ago, Earth was a young, inhospitable, and violent planet. Lightning, erupting volcanoes, and an atmosphere filled with simple chemical compounds created the perfect setting for an unparalleled cosmic experiment, the emergence of life. But how could inert matter transform into something capable of replicating, evolving, and ultimately thinking about its own origin? The key lies in prebiotic chemistry. In the primordial oceans, simple molecules like methane, ammonia, and water combined thanks to the energy from lightning and volcanoes, forming increasingly complex organic compounds. Have you ever wondered why scientists consider the primordial soup as a cradle of life? It's because in that molecular broth, the first building blocks of biology, amino acids and nucleotides, began to gather and organize spontaneously. A famous experiment conducted by Stanley Miller and Harold Urey in 1953 demonstrated that it was possible to obtain these essential compounds by replicating the conditions of primitive Earth in a laboratory. But how do we go from molecules to living cells? The answer remains partly a mystery, but experts propose that eventually some molecules acquired the ability to copy themselves, initiating evolution. Imagine a relay race where each participant improves their technique with each lap. The first forms of life, likely simple chains of RNA, began to compete, combine, and evolve into increasingly efficient and complex structures. Over time, the first cells appeared, capable of protecting and organizing their own genetic material. Thus, life became firmly anchored on our planet. And what role did cosmic elements play in this process? Carbon, oxygen, hydrogen, and other essential atoms for life were forged in the hearts of ancient stars, scattered across the cosmos after titanic explosions. Every cell, every molecule in your body, is the result of a chain of events that began long before Earth existed. Asking about the origin of life is not just a biological question, but also a story of cosmic connections. From stardust to primordial oceans, to the incredible diversity of organisms that inhabit our planet today, the emergence of life on Earth was not a unique or instantaneous event, but a gradual process filled with trials, errors, and millions of years of natural experimentation. Each step, from the first self-replicating molecules to multicellular organisms, was driven by the same physical and chemical laws that govern the entire universe. Thus, life is not just a rarity in a corner of the cosmos, but the inevitable consequence of the evolution of matter under the right conditions. Could this phenomenon be repeated on other worlds? Science is still seeking the answer, but the story of life on our planet shows that when the universe finds an opportunity, it turns it into something extraordinary. What mysterious force is pushing the universe to expand faster and faster? For a long time, astronomers believed that gravity, like an invisible hand, would slow down cosmic expansion after the Big Bang. However, in the late 20th century, a surprise shook the scientific community. The expansion of the universe not only continues, but accelerates. How is it possible that the universe, instead of slowing down, is stepping on the cosmic accelerator? The key to this mystery lies in the so-called dark energy, a form of energy that, although it represents almost 3/4 of the universe, remains deeply enigmatic. We cannot see or touch it, but its effects are unmistakable. It's as if the universe is being inflated by an anti-gravitational force that pushes galaxies farther apart faster and faster. Can you imagine inflating a balloon, and instead of needing more air, the balloon itself started to inflate on its own, faster and faster? That's how strange the accelerated expansion of the cosmos is. Where does this dark energy come from? So far, the best clue comes from observations of distant supernovae, which act as beacons in the darkness of space. These stellar explosions allowed for precise measurements of how the expansion of the universe has changed over time. The results showed something unexpected. Billions of years ago, the expansion began to accelerate, defying expectations based solely on gravity. This leads to a fascinating question. Is dark energy a universal constant, as Einstein proposed, or could it vary over time? The consequences of this phenomenon are profound. If the acceleration continues unabated, the fate of the universe will be a gradual cooling and dispersion, where galaxies will drift so far apart that, in a distant future, the night sky will be almost empty. Everything we know today, galaxies, stars, and even matter itself, could be isolated in an increasingly cold and lonely universe. The accelerated expansion not only defines our present, but also seals the cosmic future. Could dark energy be the invisible conductor of the cosmic orchestra, marking the rhythm of the universe until its end? What happens when a star runs out of fuel? This is one of the most fascinating questions in astrophysics because the fate of a star depends on its mass, as if the universe had written different endings for each protagonist. A star like our Sun, when it runs out of hydrogen in its core, begins to expand and becomes a red giant. During this process, it loses its outer layers, and what remains is a dense, hot core. A white dwarf, the size of Earth, but with a mass comparable to that of the Sun. However, this is not an explosive ending, but a slow fading. The white dwarf cools down until, theoretically, it becomes a black dwarf, although the universe is not old enough for them to exist yet. But what happens to more massive stars? This is where the story becomes truly dramatic. When a star exceeds several times the mass of the Sun, its death is much more violent. As it exhausts its fuel, gravity wins, and the core collapses catastrophically, producing a supernova. This explosion is so bright that for a brief period, it can outshine the entire galaxy in which it resides. The remnant left after the explosion depends on the original mass. It can form a neutron star, an object so dense that a teaspoon of its material would weigh millions of tons, or even, if the mass is sufficient, a black hole where gravity is so intense that not even light can escape. Did you know that some of the elements that make up our bodies, like calcium in our bones or iron in our blood, were forged in the heart of these supernovae? Each stellar explosion is like a gigantic cosmic alchemy, scattering heavy elements through space and sowing the material necessary for the formation of new planets and future generations of stars. Thus, the death of a star is not just an ending, but also the beginning of new cosmic cycles. In the end, the fate of stars is a reminder of the cyclical and transformative nature of the universe. From white dwarfs that slowly fade away, to neutron stars that spin at incredible speeds and emit powerful beams of energy, to black holes that challenge our understanding of physics, the legacy of each star remains. The next time you look up at the sky and see a twinkling star, remember that, at some point, that star will live out its own destiny, contributing to the great cosmic tapestry that connects everything that exists. Did you know that the universe is the stage for colossal encounters between galaxies, true cosmic titans, dancing in a choreography dictated by gravity? Galactic collisions are not simple crashes like cars on a highway, but processes that can last hundreds of millions of years. What really happens when two galaxies meet face to face in space? Although it may seem incredible, it is very rare for the stars within them to collide directly, because the space between one star and another is so vast that, in comparison, a galaxy could be as empty as a stadium with just a few soccer balls scattered inside. But if stars almost never collide, why are these encounters so spectacular and transformative? The key lies in the gas, dust, and gravitational force. When two galaxies approach, their gravitational fields intertwine and distort their shapes, elongating spiral arms, creating spectacular bridges and tails of matter. It is in these moments that true star formation storms are unleashed. The gas compresses and gives birth to new generations of stars, often much faster than would occur in isolated galaxies. Did you know that many of the elliptical galaxies we observe today are the result of ancient cosmic mergers? And what happens to the supermassive black holes that usually inhabit galactic centers? When two galaxies merge, their black holes also begin a slow and majestic approach, spiraling together until they finally unite into a single, even more massive colossus. This event can release gravitational waves so powerful that they distort the very fabric of space-time, waves that, with the right instruments, we can detect even millions of years later. Can you imagine the echo of a galactic collision traveling through the cosmos until it reaches us? Galactic collisions are not rare in the history of the universe. In fact, our own Milky Way, within several billion years, will merge with the Andromeda Galaxy in an encounter that will forever change the appearance of the night sky. These processes, far from destroying, are engines of creation and evolution. It is thanks to them that new stars are born, elements are recycled, and even larger structures like galaxy clusters are forged. Thus, the universe demonstrates that even the most chaotic events can give rise to beauty and renewal. What happens when the universe stops being a vibrant place filled with new stars? The answer leads us to a fascinating and little-known stage, the era of stellar degeneration. This is the time when the cosmos ages and star formation comes to an almost complete halt. Imagine it as a gigantic city that, after centuries of activity, watches as its lights gradually dim and its inhabitants become memories. During this era, the reserves of cold gas needed to form new stars are depleted, and galaxies cease to shine with the intensity of past epochs. The universe, once a stage of birth and stellar explosions, transforms into a place dominated by exotic and silent objects. But what are the protagonists of this aged universe? They are the stellar remnants, white dwarfs, neutron stars, and black holes. White dwarfs, which were once the radiant hearts of sun-like stars, now glow faintly as they slowly cool. Neutron stars, Ultra-dense cores born from supernovae spin like cosmic beacons until their energy fades. And black holes, those gravity wells from which nothing can escape, remain as the last guardians of energy and matter. It is a universe where light gradually extinguishes and cosmic silence prevails. Have you ever wondered how long a white dwarf can last before it completely extinguishes? These objects can take trillions of years to cool down into black dwarfs, bodies so cold and dark that they would be practically invisible even to the most advanced instruments. However, since the time required to surpass that transition is much greater than the current age of the universe, there are still no known black dwarfs. In this scenario, visible matter becomes increasingly cold and dim relics, while energy disperses and the universe approaches a deeper thermal equilibrium. So, what does all this mean for the final destiny of the cosmos? In the era of stellar degeneration, the universe becomes a vast cosmic graveyard. Matter collapses into compact objects, and the light of the last stars fades away. The dynamic processes that once shaped galaxies are left in the past, and what remains is a universe dominated by stillness, darkness, and the waiting for even slower phenomena, such as the evaporation of black holes. Thus, the era of stellar degeneration represents the twilight of the universe, the moment when the cycle of cosmic life enters its most silent and mysterious phase. How is it possible for something as dense and seemingly invincible as a black hole to disappear? Although it seems impossible at first glance, theoretical physics reveals a truly fascinating phenomenon: the evaporation of black holes. This idea was proposed in the 1970s by Stephen Hawking, who demonstrated that, far from being eternal, black holes slowly lose mass and energy through a process known as Hawking radiation. But how does this happen if nothing, not even light, can escape from their event horizon? The key lies in the strange behavior of the quantum vacuum, where pairs of particles and antiparticles constantly emerge and usually annihilate each other almost instantly. However, when this phenomenon occurs near the event horizon of a black hole, something surprising can happen. One of these particles falls into the black hole, while the other escapes into outer space. The escaping particle is detected as radiation, while the one trapped in the black hole takes away a tiny portion of energy and mass. It's as if the black hole is losing weight, but at an extremely slow rate. Does this mean that all black holes will eventually disappear? In theory, yes. However, the time it takes for them to evaporate depends on their mass. A stellar black hole, for example, would take many orders of magnitude longer than the current age of the universe to completely evaporate. But much smaller black holes, like the hypothetical primordial black holes, could evaporate on much shorter timescales, releasing an immense amount of energy in the form of radiation during their final moments. Imagine an invisible object for billions of years that in its last moments explodes with tremendous power. Hawking radiation not only challenges our intuition about black holes, but also raises one of the greatest enigmas of modern physics: the information paradox. If a black hole evaporates and disappears, what happens to all the information about the matter that once fell into it? Is it lost forever, or does the universe find a way to preserve it? This question remains a topic of debate among physicists, and its answer could revolutionize our understanding of the cosmos, gravity, and quantum mechanics. Ultimately, the evaporation of black holes reminds us that even the most extreme objects in the universe are subject to the laws of quantum physics. Nothing is truly eternal, not even a black hole. The study of this process brings us closer to the boundary between the known and the unknown, showing us that the universe always holds surprises beyond imagination. What will happen to matter when the stars have died and black holes have evaporated? To understand the ultimate fate of the cosmos, it is essential to explore the role of protons, those tiny particles that form the nucleus of every atom in the universe. For decades, scientists have wondered, are protons truly eternal, or do they also have an expiration date? The standard model theory suggests that protons should be stable, but some theories beyond this model such as certain variants of grand unification, predict that protons could decay, albeit on timescales so long that they defy imagination. We are talking about more than one followed by 34 zeros of years. What does proton decay entail? Imagine that protons, as fundamental building blocks of matter, begin to slowly crumble, releasing lighter particles and energy in the process. If this were to happen, all ordinary matter, from rocks to stars and living beings, would gradually fade away, leaving behind an almost empty universe. Experiments in underground laboratories, such as Super Kamiokande in Japan, are searching for signs of this possible decay, but so far they have found no conclusive evidence. However, the mere possibility that matter is not eternal radically changes our view of the future. If protons are indeed unstable, the universe would undergo a slow but inexorable transformation. The atoms that today form planets, dust, and interstellar gas would simply cease to exist. The process would be so gradual that in comparison, the life of a star would seem like a blink. But if protons were absolutely stable, matter could persist forever, albeit in an increasingly cold and dispersed state, dominated by cosmic expansion and entropy. What is the final fate of matter? The answer depends on whether protons decide to rebel against eternity or not. If they decay, the universe will end up being a vastness of light particles and radiation, with no atoms, no structures, just a distant echo of what once existed. If they do not, matter could survive, but in an increasingly lonely and cold cosmos, where energy dilutes almost to the point of disappearing. Whatever the outcome, the fate of protons is one of the great unknowns that will define the final chapter of cosmic history. What will happen when the universe reaches its old age? Astrophysicists call this period the dark era of the future, a stage in which stars, those tireless factories of light and heat, will have exhausted their fuel and will extinguish one by one. Without the presence of new stars being born, the cosmos will be plunged into deep darkness, inhabited only by the remnants of what was once a vibrant and energetic universe. Is it possible to imagine a universe without any visible source of light, only the cold and silent echo of its own past? In this era, the protagonists will no longer be bright suns or active galaxies, but compact and silent objects, white dwarfs, neutron stars, and black holes. All these stellar remnants will wander through an increasingly cold and empty space. The planets, if they still exist, will be lonely worlds, orbiting stellar corpses, shrouded in perpetual twilight. Without light, the temperature of the universe will continue to drop, slowly approaching absolute zero. What happens to matter in a universe where time seems to have frozen? Little by little, even these vestiges will begin to disappear. White dwarfs and neutron stars, after inconceivable eons, may transform into even more exotic objects like black dwarfs, bodies so cold and dark that they would be completely invisible. Black holes, for their part, are not eternal either. They will gradually release their energy in the form of Hawking radiation, evaporating until only a trace of scattered particles remains. Can nothingness truly be the final destination of everything that has existed? In the dark era of the future, the universe will be an ocean of solitude and silence, where the information and complexity that once flourished will have been replaced by disorder and total dispersion. It is like contemplating a grand theatre after the last performance. The lights go out, the actors retreat, and only the echo of what once was remains. Is this the definitive end, or just a pause before a new cosmic cycle? Although science does not yet have all the answers, understanding this era invites us to reflect on the fleeting nature of existence and the inevitable march of time toward darkness. What if the universe didn't have an explosive end, nor a dramatic collapse, but simply faded away slowly, like a campfire extinguishing without a sound? This is the hypothesis of the Big Freeze, one of the most fascinating and cold scenarios for the final fate of the cosmos. In this scenario, the expansion of the universe not only continues, but accelerates due to the mysterious dark energy. Everything moves away from everything, and the distance between galaxies grows until, eventually, space becomes so vast and empty that communication and interaction between the last islands of matter become impossible. Why is it called the Big Freeze? The name is not an exaggeration. As the universe expands, energy disperses, and the average temperature of the cosmos drops to unimaginably low levels. Atoms, stars, and even black holes end up radiating their remaining heat, cooling down in a process that lasts far longer than the lifespan of any star. Eventually, even light goes out. In this scenario, the universe becomes a place dominated by darkness and silence, with a temperature so close to absolute zero that any form of life, as we know it, would be completely unviable. Can you imagine a universe where even atoms are not eternal? In the Big Freeze, decay processes continue to act over nearly unimaginable timescales. It is estimated that, after trillions of years, protons could begin to decay, leaving behind only radiation and scattered subatomic particles. Black holes, once the titans of the universe, will end up evaporating through Hawking radiation, slowly disappearing until all that remains is a sea of photons and elementary particles, extremely cold and lonely. Is there any hope that something might emerge in this frozen universe? The answer, according to what we know today, is no. Entropy reaches its maximum, disorder is total, and there is no usable energy left to form new structures. The universe, in this scenario, does not end with a bang, but with a whisper, an infinite and silent freezing where time continues to flow, but nothing relevant happens again. Thus, the Big Freeze represents the most desolate and at the same time, the most poetic image of the final fate of everything that ever existed. What would happen if the universe, instead of expanding forever, decided to change course and collapse in on itself? This scenario, known as the Big Crunch, has fascinated scientists and curious minds for generations. The idea stems from a fundamental question. Will gravity ever be strong enough to halt cosmic expansion and reverse it? If the answer is yes, then everything we know, galaxies, stars, and planets, would begin a slow but relentless fall towards a common endpoint. To understand this possible fate, it's key to imagine the universe as a balloon that we have been inflating. If the amount of matter and energy inside is sufficient, there will come a time when the internal pressure can no longer sustain the expansion, and instead, the balloon will start to deflate. Similarly, in the Big Crunch, the gravitational pull of all matter and energy would surpass the force driving the expansion, causing the universe to contract faster and faster. During this process, galaxies would move closer together, temperatures would rise to extreme levels, and the density of matter would grow exponentially. Clusters of galaxies would collide, stars would merge into a gigantic cosmic soup, and as space became smaller, even atoms would be crushed. Could, at that moment, the physics as we know it continue to function? Or, just like in the early moments of the universe, would there be new laws and phenomena yet unknown that would dominate this end? One of the most intriguing questions is what would happen right at the final moment. If the entire universe is compressed into a point of infinite density, would this be the true end? Or could it give rise to a new Big Bang? Some scientists have proposed that the Big Crunch could merely be the beginning of another cosmic cycle, a sort of universal reset where the collapse leads to a new expansion. However, the actual fate depends on factors such as the amount of dark matter, the influence of dark energy, and the true geometry of space-time, elements we are still far from fully understanding. The Big Crunch remains one of the most dramatic and mysterious hypotheses about the fate of the cosmos. Although current observations favor an accelerated eternal expansion, the possibility of a future where everything that exists comes back together into a single point reminds us how little we truly know about the ultimate nature of the universe. Is the universe an endless cycle of births and destructions, or are we doomed to a unique and irreversible end? For now, the answer remains hidden in the depths of time and space. What if the universe not only expanded forever, But that expansion became so fast and violent that it literally tore apart all matter. This is the unsettling hypothesis known as the Big Rip. But is it really possible for the cosmos to end in absolute destruction, where even atoms are ripped from themselves? To answer this, we need to explore the mysterious role of dark energy, that invisible force responsible for accelerating the expansion of the universe. Unlike matter and radiation, dark energy seems to have a strange property. Its density does not decrease as the universe grows. What does this imply? Imagine the universe as a loaf of bread that is inflating in the oven, but in this case, the heat keeps increasing and causes the bread to explode. If dark energy increases its strength over time, there will come a point when it surpasses gravity, nuclear force, and even the forces that hold atoms together. The result would be a future in which first galaxies, then stars and planets, and finally molecules and atoms would be torn apart one by one. What would it be like to experience the Big Rip? If the theory is correct, in billions of years, the most distant galaxies would disappear from our view because they would be moving away faster than light can reach us. Shortly after, the stars that make up our galaxy would separate and planetary systems would collapse. Finally, in the last minutes, Earth would be shattered and the very atoms that form all matter would be disintegrated. It's a truly dramatic ending, as if the universe were unraveling into nothingness. Is there evidence that this will happen? For now, the Big Rip is just one of several theoretical possibilities. It depends on the exact nature of dark energy, which remains one of the greatest mysteries in physics. If this energy behaves even more exotically than we imagine, the Big Rip could be the ultimate fate of the universe. However, if its strength remains constant or decreases, other scenarios like the Big Freeze or the Big Crunch would be more likely. In any case, the Big Rip reminds us of how little we know about the cosmic future and how shocking the ultimate fate of everything that exists can be. What if the universe is not a one-way journey, but an endless cycle of cosmic births and deaths? Here arises one of the most fascinating ideas in modern cosmology: the Big Bounce. Can the universe be reborn from its own ashes? This hypothesis suggests that the current universe is neither the first, nor will it be the last. Imagine a cosmic ball that, instead of stopping when it hits the ground, bounces back propelled by titanic energies. Thus, after a total collapse, all matter and energy compressed into an infinitesimal point would give rise to a new Big Bang, and so on, in an eternal dance of expansion and contraction. But what evidence supports this bold proposal? The Big Bounce theory emerges as an alternative to the traditional idea of a single Big Bang. Some quantum models of gravity suggest that upon reaching maximum compression, the laws of physics, far from allowing an infinite singularity, act like a cosmic spring. Instead of an abrupt end, the universe finds a quantum limit that propels it to expand again. It's as if the universe has a memory of its previous cycles, avoiding the abyss of nothingness and transforming collapse into new creation. Can current physics verify this eternal cycle? So far, there is no direct evidence, but scientists are searching for traces in the cosmic microwave background, in the large-scale structure of the universe, and in the patterns of gravitational waves. If the universe has experienced other cycles before ours, there could be subtle signals, like wrinkles in primordial radiation or echoes of ancient bounces. However, the vast majority of the data observed so far fits better with a universe that began with a single Big Bang, although the mystery remains open. What is the philosophical significance of a universe that never ends, but reinvents itself time and again? The Big Bounce challenges the notion of an absolute beginning and a definitive end, proposing a cosmology where destruction is merely the prelude to new creation. If this vision proves true, the universe is like a cosmic phoenix. Each death is merely the prelude to a rebirth, and the history of the cosmos would be an infinite symphony of cycles, where each end is, in fact, a new beginning. Have you ever wondered if our universe is truly unique, or if, somewhere beyond the imaginable, there are other universes with their own laws and realities. This is one of the most fascinating questions in modern cosmology and leads us directly to the concept of parallel universes and the multiverse. The idea may sound like science fiction, but it has roots in serious scientific theories. For example, according to cosmic inflation theory, during the first moments after the Big Bang, space may have expanded so rapidly and chaotically that it generated bubbles, each with its own universe, its own physical laws, and even distinct fundamental constants. What would this imply? If the multiverse exists, we could imagine that in other universes gravity is stronger, light is slower, or even that matter as we know it does not exist. It's as if our universe is just a drop in an infinite ocean of alternate realities. In fact, some physicists propose that there are different types of multiverse. One of the most discussed is the level 1 multiverse, where space is so vast that somewhere, very, very far away, there exists another Earth almost identical to ours, but with small differences. Other models, like the level 2 multiverse, suggest that fundamental laws may vary completely between universes. Why do scientists take these ideas seriously? In part, because certain quantum and cosmological theories, such as quantum mechanics and string theory, predict the possibility of multiple universes. For example, in the quantum world, every time a decision occurs, the universe could split into different branches, creating parallel realities where every possible outcome takes place. This interpretation, known as Everett's parallel universes, suggests that somewhere there exists a universe where you made different decisions than the ones you made today. Furthermore, in string theory, the existence of additional dimensions could lead to completely separate universes from ours. Does it make sense to look for signals from other universes? So far, there is no direct evidence of their existence. However, some scientists have proposed that certain anomalies in the cosmic microwave background, the fossil radiation of the universe, could be traces of collisions with other universes. If such a signal were ever detected, it would completely revolutionize our understanding of reality. The mere act of asking ourselves if we are just a small part of a multiverse challenges our ideas about space, time, and the ultimate fate of everything that exists. The possibility of parallel universes not only broadens the horizon of science, but also invites us to view the cosmos with a mix of wonder and humility. What exactly is entropy, and why is it so crucial in the history of the universe? Entropy, in simple terms, is a measure of disorder or randomness in a system. But beyond a simple definition, entropy dictates the fate of absolutely everything that exists. From the heat dissipating in a cup of coffee to the evolution of entire galaxies, entropy is the great invisible conductor of the cosmic orchestra. Why do we never see heat flowing spontaneously from a cold object to a hot one? The answer is entropy. It always tends to increase, guiding the universe toward an increasingly disordered state. Now, how does entropy affect the universe as a whole? Imagine the cosmos as a gigantic party that started with everything perfectly ordered. At first, energy was concentrated and the possibilities were infinite. But with every passing second, that energy disperses and disorder grows. Stars are born, shine, and eventually die, releasing their energy into space. Galaxies group and collide, mixing matter and energy in a chaotic dance. This entire process is the manifestation of entropy in action. The universe is slowly heading toward a state of thermal equilibrium where it can no longer perform useful work. But does this mean that the universe is doomed to eternal boredom? Entropy is not just a destructive force, it also drives cosmic creativity. Thanks to energy gradients and the tendency toward disorder, new structures and phenomena emerge, from gas bubbles collapsing to form stars, to planets that harbor life. Without entropy, change would be impossible. It is paradoxically the engine of chaos and the source of the temporary order we observe in galaxies, solar systems, and of course, in ourselves. However, entropy poses a troubling question. What is the final destiny of everything? If entropy never stops increasing, there will come a time when the entire universe is so dispersed and cold that there will be no way to extract energy from anywhere. This scenario, known as thermal death, would be the final act of the cosmos, when matter and energy reach their maximum equality and time loses its meaning. Thus, entropy is not just a physical law, it is the silent narrator of the universe's story, marking the rhythm of every transformation, from the first moment to the last cosmic breath. Did you know that the universe has a temperature? Although space seems cold today, it actually still retains a slight residual heat, the cosmic microwave background. This radiation bathes the entire cosmos, and its temperature is just 2.7 kelvins, which is a little over 2 degrees above absolute zero. If we had a perfect thermometer and left it floating far from any star, that would be the temperature it would register, reminding us of the heat from the Big Bang, an explosion that occurred over 13 billion years ago and is still felt in every corner of space. One of the most intriguing questions is, are there more stars in the observable universe than grains of sand on all the beaches of Earth? Although it sounds incredible, astronomers estimate that there are more stars, perhaps even 10 times more. If you tried to count the grains of sand on a single beach, it would take you more than a lifetime. But in the cosmos, the number of stars far exceeds that figure. Each of those stars could have planets around them, leading us to another curiosity: rogue planets. These are worlds that wander alone through space, unbound to any star. It is estimated that there could be more rogue planets than stars, traveling in the darkness, invisible and mysterious. How do we know that the universe is mostly made up of things we cannot see? More than 95% of the cosmic content is invisible to us. Dark matter and dark energy dominate the mass and energy of the universe. Even though they do not emit or reflect light, their presence is only detected by gravitational effects and the acceleration of cosmic expansion. Can you imagine trying to assemble a giant puzzle of which you can only see a small part of the pieces? That's the task scientists face when studying the universe. Most of it remains hidden behind an invisible veil. The timescales in the universe are also astonishing. For example, the light we see from some distant galaxies began its journey when dinosaurs still roamed the Earth. Looking at the sky is looking into the past, as light, although fast, takes millions or even billions of years to reach us. Additionally, there are stars called white dwarfs that may take longer to cool completely than the universe has existed so far. And speaking of extremes, supermassive black holes can contain the mass of millions or even billions of suns, concentrated in a space so small that it defies all logic. Finally, a curiosity about the future. Although it seems immutable, even protons, the fundamental building blocks of matter, could someday disintegrate. If this happens, within a time span that defies imagination, all the matter in the universe could fade away, leaving only energy scattered in an ocean of emptiness. Thus, the universe shows us that it is not only vast and inexplicable, but also deeply mysterious in each of its eras and corners. What does the future hold for us in the exploration of the cosmos? Throughout history, humanity has looked to the sky for answers, but today we find ourselves at a turning point. Never before have we had so much technology and so many unanswered mysteries. Are we close to finding life beyond Earth? New space telescopes, like James Webb and the upcoming next-generation observatories, will allow us to observe the atmospheres of exoplanets and analyze their composition in search of chemical signatures that could reveal the presence of living organisms. Just as a detective searches for clues at a crime scene, astronomers scrutinize the light from distant stars to decipher whether life has flourished in some corner of the universe. But exploration is not limited to observing from afar. Upcoming missions plan to return to the Moon with humans and establish permanent bases, while Mars looms as the next great destination. What challenges await us in the colonization of other worlds? Radiation. the lack of a breathable atmosphere, and distance are formidable obstacles. But research in biotechnology, robotics, and sustainable energy is advancing rapidly. Perhaps in a few decades, growing food in Martian soil or extracting water from its subsurface will cease to be science fiction and become routine for the first colonizers. On a cosmic level, the search for dark matter and dark energy promises to revolutionize our understanding of the universe. More than 90% of the mass and energy of the cosmos remains invisible, detectable only by its gravitational effects. What are these mysterious components really? Experiments like the Large Hadron Collider and underground detectors seek elusive particles, while space observatories refine the measurement of universal expansion. Solving this enigma could trigger a new era in physics, as groundbreaking as the discovery of relativity or quantum mechanics. And there remains one fundamental question: will we ever be able to travel beyond our solar system? The development of solar sails, interstellar probes like the Breakthrough Starshot project, and research in advanced propulsion open the possibility that one day a human ship will cross the interstellar abyss to other stars. Although for now these projects are merely dreams and prototypes, the history of space exploration is filled with impossibilities turned into achievements. The future of cosmic exploration is, in essence, the promise that the universe still holds surprises for those who dare to seek them. What does the passage of time in the universe really mean? By observing the cosmic eras, we realize that the universe is a stage in constant transformation where nothing remains the same. From the moment space and time emerged to the boldest speculations about the ultimate fate of the cosmos, each stage shows us that change is the only constant. But what role do we play in this story of billions of years? We often think of the universe as something immutable and eternal, but in reality, it is like a gigantic clock that never stops, with its gears being the laws of physics and entropy. Have you ever wondered why everything tends toward disorder? Entropy is the universe's natural tendency to move from organized states to chaotic ones. And from that dance, stars, planets, and ultimately, life itself are born. It is astonishing to think that the very energy that makes a star shine is the same that, in the distant future, will contribute to cosmic silence and darkness. Each cosmic cycle, from the formation of elementary particles to the birth and death of galaxies, has been an opportunity for the creation of new structures and phenomena. If the universe were a book, each era would be a chapter filled with challenges, surprises, and unanswered questions. Is this the only possible universe, or are there infinitely more beyond our horizon? Will the cycle continue, or will it reach an irreversible end? Science, like the explorers of old, tries to decipher these mysteries, but new uncertainties always arise. Perhaps the most fascinating thing of all is that, for a brief moment, matter organized itself in such a way that it was capable of contemplating itself. We, made of stardust, are witnesses and narrators of this great cosmic story. The ultimate fate of the universe remains an enigma, but our curiosity and capacity for wonder drive us to keep exploring. In the end, the cycle of cosmic existence is not just a matter of astrophysics, but also an invitation to reflect on our own place in the vast tapestry of the universe. What other wonders await us in the upcoming chapters of this endless story?